Students, actually, the last meeting was actually continuing, so I couldn't end it. Whatever. So now I think you have understood the working formula of the experiment, and the circuit diagram is very simple over here. And now I'll show you how to take the readings. Okay, so there, as I told, there are two parts in this experiment. First part is to find out the resistance of the galvanometer. Okay, the galvanometer, table galvanometer, these are actually table galvanometer. Okay, there are other different types of galvanometers. I'll say about it at the end. So for this particular table galvanometer, I'm telling you that we'll find out the resistance of the galvanometer first with one certain formula, and that G equals to this formula. If you see, G equals to Rs by R minus S. This is the formula. G equals to Rs by R minus S. I had just shown you in the last class that how is this coming. Rs by R minus S. Using this formula, we'll find out the value of G using half deflection method. And after that, using this value of G, we will use it in the second equation to find out the value of figure of merit K. This way, we will perform this experiment. Now let us come to the circuit once. Please see the circuit over here. For the first part, for finding the resistance of galvanometer. In this circuit, let me tell you once more, the different circuit elements are, this is the power supply, DC regulated power supply, this one. And we can keep a value of the supply voltage from 0 to 6 volt in this within the range, and connected to a key in series. After that, there is a galvanometer in series in the circuit, and then a high resistance box is also connected in the circuit. And another shunt, a low resistance in parallel, that is called a shunt, is connected across the galvanometer with the help of a key, certain key. That means if the key is on, then S is active, S will be counted in the circuit, and if the key is off, then S will not be counted in the circuit. This way, this is a very simple circuit. So this is the required circuit for finding the resistance of the given galvanometer. So let us see the circuit once now. So this is the circuit as we have made as per the diagram. Okay, let me show you the circuit elements one by one. This is the DC regulated power supply. This is a high resistance box. I've shown you, this is another sample is kept over here. You can see this. You can see the values, these values. So starting from 1 ohm, 2 ohm, 2 ohm, 5 ohm, 10, 20, 50. So the values are in the ratio 1 is to 2 is to 2 is to 5. That means you will have 1 ohm, 2 ohm, 2 ohm, 5 ohm, then you will get 10, 20, 20, 50, then 100, 200, 200, 500. In this way, all the values are you'll get, because this ratio has a certain uniqueness. Can you say anybody what is the specialty of this ratio? 1 is to 2 is to 2 is to 5. In the weight box also, we have all the weights in this ratio, 1 is to 2 is to 2 is to 5. What is the specialty of this particular ratio? Can anybody guess? Rakesh, Debanjan, other students?
All other weights can be found by combining these two in different ways.
Yes, we can have any values by combining all these values. 1 is to 2 is to 2 is to 5. We can from 1 to 9, from 1 to 9, 1 is to 2 is to 2 is to 5, all can be made. Similarly, from 10 to means 19, all can be done. So this is a unique ratio. Okay, whatever. This way, the resistance box, all the resistance are kept like this. Now let me brief you a little bit about this. Then I am coming to the circuit. Because we have to know each element nicely, otherwise how can you use it in the circuit? So this is called a resistance box. The range is starting from, as I can see, and you can also, I think, 1 ohm to, it is 100 ohm. This will be 500, 200, 200, sorry, 5000 ohm. Okay, 1 ohm to 5000 ohm. This is the range of the, it's a high resistance box. You can have other resistance box of different ranges also. As we are using as a shunt, a low resistance box. Here also the values are 1 to 10, 1 to 10, 1, 2, 2, 5, 10, infinity. So these are the values. So resistance box of different range are available. Now, as per the requirement, we use it in the circuit. Now, let me tell you how does it work? How does the resistance box work? Actually, inside the resistance box, okay, there is a resistance coil inside, okay, and the coil is wrapped, one after another coil is wrapped. Now, see this once. I have opened this key. This key is in the value, corresponding value is written over here, 50 ohm. Sir, focus a little bit. This value is 50 ohm. Okay. Okay. This value. Okay. Is it visible? Sorry, out of the camera. Okay, okay. The values are written, you have seen. A resistance box in class 10 also you have seen. Whatever. Okay, sir. Okay, leave. So this is 50 ohm written. So now if this key is taken out from the box, then we can say in the resistance, in the circuit, 50 ohm is applied. How it is possible? Okay. The thing is that, let me draw something for this. Wait. So please focus this side. This formula I am erasing because it is already written in your copy. So this part I am erasing. Actually, let me show you. In this box, this metal base I am drawing first. The metal base is like this. Okay, and each key is placed inside the metal base. Like this. Okay, so in that case, the resistance wire is connected here. Actually, it is wrapped over here. Okay, the resistance coil, the coil is wrapped over here. Now the thing is that, and it is connected, there are two terminals actually, then it is coming to here, then it is wrapped over here, then coming to here. This way it is going on. And there are two terminals, you can see. Okay, so this is the path of the current. Actually, current will flow like this through the resistance. Now the thing is that, if this is inserted, if the key is inserted like this, if the key is inserted, then this is also having a metallic base. Leg is the metallic one. Okay, so it is shorted. It is shorted means the current will pass directly through this. Means it will not take the coil. It will not take the coil. The current will not pass through the coil over here, which is over here. Okay, but if the key is taken out, then the current will pass through the coil, and that coil has certain resistance, and that resistance is effective in the circuit. Okay, so just by giving this, when 50 ohm is written over here, and I have taken out this key, which indicates that the current is passing here, it is shorted, completely shorted. After that, the current is passing to the coil inside, and then again it is coming to this side. This way the path is complete. So here the current is passing through the coils, and the coil has corresponding resistance of 50 ohm. It has been this has measured earlier only, and then the values are written. This is called the calibration of the box. This process is known as the calibration, where the resistance values are written. Sometimes it can have some error also, whatever. So this 50 ohm resistance is effective now in the circuit if I am taking it out, because the current is passing through the inner coil. But if I put it over here, then it is shorted, then the current will pass, it will not take the coil, it will just pass through the leg, that metallic leg. So the resistance is 0 over here. Okay, like that, it is completely sorted circuit like that. So this way a resistance box works. Okay, so now let me tell you after that. So this is the circuit. See the circuit diagram and this actual circuit preparation. Okay, first you see the circuit diagram. Let us start from here. From the positive terminal of they all are in series. They all are in series, and I think you have this basic idea that since they all are in series, they can be placed anywhere in the path. Okay, there means you may break the sequence also. Ultimately they will be in series because the current is passing through the same path only. There are no branches. So whatever, here the DC power supply is there, whose positive terminal plus is here, and then it is connected to the high resistance R. It is connected to the high resistance box R. Then from R, it is connected to the positive terminal of galvanometer. Let me tell you, this is plus, this is minus. Why? Because this terminal is connected with cell positive and this is cell negative. So this is plus, this is minus. Then with a certain key, again going back to the cell negative. This is the complete circuit. Now the shunt is connected in parallel with the help of a key. This is the on off switch with the help of a key. Okay, so this way the complete circuit is made. Now let's see here. This is the positive terminal of the cell. Your eye should be on the circuit as well as here. So please focus both together. Hmm. So this is the positive terminal of the cell, this red button, this one, positive terminal. Then any one terminal of the resistance box. Resistance box does not have any plus minus terminal. It does not have any polarity. So you can connect anywhere. So this is the terminal. After that, from here, it will go to galvanometer plus. This is red is plus. Then galvanometer minus, negative to, through the key, it will go back to the cell negative. So this circuit is made. This circuit is made. Now with the positive galvanometer, a shunt is connected with the help of a key. And this is the shunt part from positive side. This is the shunt resistance, low resistance. Then it is going back to the negative terminal through a key. Okay. So there are two keys used in the circuit. First key is K1, which is the main key of the circuit, which is here. Is the main key of the circuit, which is connected directly to the with the cell. Means if this key is off, then everything is off. No passage of current in the circuit. The cell is actually off. So this key is on, and this can be on and off just to activate or deactivate this shunt resistance S. Okay, this is the entire circuit. Very simple thing it is. Okay. Now, as I told that I'll show you one or two, maximum one or two observations over here, so that just to explain you how to take the readings. Okay, then rest of the readings you will get. So first, as I told that before, after making the circuit, please don't switch it on. First, what you have to do, because if we switch on, these are very common questions in Viva. What you will do after making the circuit, what you will do. And if you say, sir, I'll switch on the circuit, then so it's gone. So you have to say, first, I have to take the proper precaution. So that the galvanometer is protected. That is very important. You have to protect this galvanometer. So high current should not pass. Means if you are not taking any value of resistance from this resistance box, then as per the voltage given over here, a high current will flow, and that current might be greater than Ig, as I discussed in the last class. Okay, it might be greater than the full scale deflection current flowing through the galvanometer. So we have to keep this in mind that I should not exceed Ig value. For that reason, we have to do certain calculation in the copy. Like we know that the value of E, how much E I am keeping in the cell, that I know because I am only keeping it. Suppose it is 4 volt. So taking this as 4 volt, okay, Ig value will be supplied to you, Ig value. Okay. Then taking that Ig value, you have to put the value of R, and the formula that I had written, equation number 1, if you see your copy, E by R plus G, I equals to E by R plus G. That formula here you see once, I equals to E by R plus G. So with the help of this formula, okay, this should be Ig, this should be basically Ig. Okay, so for what value of R you have to choose, means first see basically trial and error method, because initially you don't know the value of G because you are finding it. Okay, you are finding it only. So you can take a value of 5,000 to 5,500, 6,000. The more value you will take, more you are safe. The circuit is safe, the galvanometer is safe. That is the main thing. Okay, so keeping that in mind, see here now. Now see the thing. First, I have made the circuit. Circuit is made over here, as I have explained. Then, actually, the resistance box is inverted. You try to see. Here we have taken. Here all the resistances are in series. They all are connected one after another. As I have drawn in the diagram, resistance box, they all are in series. Okay. So whatever values you are taking out, whatever keys you are taking out from here, those resistance values are getting added. So suppose here I have taken 2000 plus 2000 plus 1000, that means 5000, 500, 200, 5700. I have taken out a resistance of 5700. Okay, just see the values. 5700. It is just getting added, nothing else. Now after taking this resistance, now I can switch on the circuit. Okay, now let's see what happens. Now I am switching on this power supply. Okay, now let me show you. This key K1 is on, but K2 is open. I don't require the shunt now. Let the shunt be connected like this, but since the key is open, so it is not active now. So what I will do now, this K1 is on, I am switching on this one. already protection I have taken. I have put the mask, now I am just going out like that. Okay. Now see the galvanometer. Okay. Again I am doing the same thing, just I am repeating. Wait, I am switching it off once more. It will take some time actually, because uh, hmm, some damping force is also there. It is actually preventing this to come back to 0. Now you can see it is coming back. Let us wait for a while, let it come to 0. Okay. So almost it is, there might be some error. Okay. Now just see once again what I am doing. I am just switching on this one. Once again you see this. Okay. So as I switched on, this current is less than Ig. So you just tell me what is the deflection over here? How many divisions it has gone? How many divisions? Tell me. Is it still moving?
Almost 20.
19.
Okay. Okay.
19.
Okay. 19. Actually, I am seeing from side, so I can't see. 19. 19 division. So you have to take the division which it has crossed. If it is in between 19 and 20, then you have to take 19. Okay, let me see the feedback. It is just, you can say 19 actually, because if it has not gone to 20, then you should not take that. Okay, so take the 19 value. Sometimes it can coincide exactly on a particular division, then that value, there is no confusion. But if it is in between two readings, then the rule is we have to take the reading that it has crossed. So we have to, if it is not 20 exactly, then take 19. Okay. So this is the value of theta. So just see, now you see the observation table. We are doing the first observation. See the observation table for the first part. Resistance of galvanometer. Serial number 1. Resistance R has been chosen over here. It is, you will write over here, how much value you will write? 5700. It will be in ohm. Table is already made with you. 5700 ohm that we have chosen. And the deflection is here, what we have seen, 19. Try to keep it an even number. Okay, try to keep this deflection in the even number, then you can have a half deflection exactly. Okay, so 19, or if it is, suppose just for the sake of convenience, I'm taking it as 20 for the timing, suppose, because the deflection is in our control. By choosing the proper value, there are small resistances also in the box, 1 ohm, 2 ohm, so that one division deflection we can manage by choosing from 1 ohm, 2 ohm, 5 ohm. Okay, so after 5700, I can take out some resistance of, means what I want to do, try to understand. Deflection is 19, I want to make it 20. So I want to increase the current through the galvanometer a little bit. Okay, so what should I do? Shunt resistance I have to increase a little bit, so that less current pass through the shunt, some more will pass through this. Okay, so now the thing is that now actually I am adjusting R value, sorry, not the shunt, sorry, the R value I am adjusting. So just by adjusting the value R over here, I can control a small amount of current also. So from 19 to 20, that easily we can manage. Okay, shunt is not yet done. Now this is the first part. Second part, I have to choose a value from the shunt resistance, such a value so that the deflection comes to 10. Why it will come to 10? Because if I choose some value from here, it is a low resistance in shunt, then some part from the current which were entering through the galvanometer, some part is coming through here also. So now the current through the galvanometer will decrease. As I am taking some value from here, the current through the galvanometer will decrease. How much to decrease? Half of the previous value. That is our purpose. Half of the previous value. That means if the previous deflection was 20, now the deflection to be made as 10. So as per the shunt value, we have to choose. Okay. So first what we will do now, first we will switch on the key and we will give the shunt value. Now let me show you one thing. If the shunt resistance all are here, that means it is having a zero resistance now. If I switch on the key, it will remain same. The deflection will remain same. Don't change the R value. R will same as the earlier value. Only S I am introducing. Okay. So when this key is on but no resistance is taken from shunt, that means zero resistance, that time the galvanometer deflection is not changing at all because it is same only. Now I have to take some resistance. Okay, so let us do that. Suppose sir, I think one this is to be connected. 50 ohm resistance is equal 50, 55 like that. So we have to replace the shunt actually with another resistance box. Let me show you this. Just wait. This is a fractional one, very small one. That is, it will not work actually, I think. Acha, while connecting this ones, please see here. When I'm connecting the wire, this insulation, this cloth insulation should not come inside. Then it will not be connected properly. So you take a piece like this. This is the actual wire, conducting wire, copper wire, and then you connect like this. Here also the same thing. Hold it like this so that the wire, this cloth should not come over here. Okay. Insulation should not come in between the key and the wire. Okay. Now I'm giving K1 so as to activate the cell, and automatically the deflection will be in the previous position. You see the deflection again in the previous position. Okay, just by giving K1 again. Means I have not switched off the power supply, only K1 I had taken out. Now it is again here. Now I have to make the deflection, I have to make it, to 10 because it is 20. So I have to make it at 10. Okay. So I have to choose some value from here. Say let us take, oh sorry, I have to give the key. Let me first give the key. K2 key, let me give first. It will come to 0. This is one observation that you see. Then I am going to ask you this. Whenever the K2 key I am giving, that the pointer comes to 0. So can you explain this? Why it is happening? Can anybody explain this one? See here once on the board. See once here. When I have not taken out any resistance from S and but given the key, then it is a shorted path. Now full current is passing through this only. No resistance has been taken out from here. So no current is passing through the galvanometer. The entire current from here is passing through this only, because I have not taken out any resistance from S. Okay. So as soon as I am giving the key K2, this circuit is active, this path is active, but there is no resistance in this path. Maybe there is a resistance box S, but I have not taken out any resistance. So the full current is passing through this only, because current always follow the least resistance path. Okay. Galvanometer has certain resistance, which we are going to find out. So it is having very less resistance compared to this, because no keys are taken out, almost zero resistance. So the entire current will pass through this. So galvanometer deflection came like here to the 0 position. Now I have to take some resistance just to make the deflection once again to 10, because earlier it was 20. So now I am taking out some values from the shunt resistance box. I am taking out first 50 ohm. Let's see. Now see the galvanometer. I have taken out 50 ohm. Is it 10 now? Can you see?
Yes.
Okay, okay. Now the deflection became half of the previous value. So I'll write over here in the table. So please focus here in the table. Shunt I have taken 50 ohm, and the deflection is 10 now. So what is the capital G value? Capital G value is RS by R plus S. That means 5700 into 50 by 5700 minus 50. So this is the calculation for capital G. This value, sir, please focus here. G equals to 5000 RS by R minus S, 5700 into 50 whole divided by 5700 minus 50. This is the value of the resistance for the galvanometer. This is the first observation. This way we will carry on. Carry on means in the next observation what we will do? In the next observation we will take some different values of R. Okay, we may increase the value of R, that is safe. If we decrease, then current in the main circuit will increase and it can exceed the IG value, that we have to keep in mind. So better you can move just round about this, I mean 5800, 5600, okay, just change by little amount, that is safe for the circuit. So if you do that, then again the deflection will be something different. Say that if you do it, for example, 5600, you are decreasing the resistance in the circuit, so the current will increase. Suppose the deflection becomes 24. Now shunt is required, some different shunt to make it 12, so some values will be over here. So similarly we can have different sets of readings, and for different observations we can have different values of constant for the galvanometer, and finally we will take the mean, the average value of the resistance for the galvanometer. Okay, so this is the first table. This way we can measure the resistance of the galvanometer. Okay, any doubt is there? Have you understood?
Yes, sir.
Okay,
Yes, sir.
okay, fine. Then in the next one, then in the next table, you see the next table now. In the next table, that K2 key is open. K2 key is open in the next table. That means there is no function of S. It may be in the circuit, but the key will be open. So what I'll do now, I'll open the key K2. And in between the experiment, when the this is on, when the power supply is on, that time capital R should be always there in the circuit. Do not, I mean, put the keys over here, then galvanometer can burn. Please remember this one, because if the current exceeds the value of IG, then more current will pass and the coil can tear also from there. So in that case the R should be always there, this capital R. So now the R value, as I have told, 5700 over here, and K2 key is open. Now there is no function of this shunt. Okay, let it be here. Now the thing is that first observation, suppose this one only, here some voltage is there, it is given over here 1.5 volt. You see there is a white mark. Can you see this? I think there is a white mark over here. This is the pointer, and it is pointing towards 1.5 volt. It is pointing towards 1.5 volt. This one, 1.5 volt. Now I am writing the first value, E equals to 1.5. Here we can vary the supply voltage. We have that option. So 1.5 volt. Now resistance, how much we have taken? Capital R, 5700. This is already taken, 5700 ohm. And what is the deflection over here now? As you told, 20. I am taking it as 20. Deflection in the galvanometer. Is it? It is 20, almost 20. Okay, just for the timing we are taking 20 theta. Okay, this is 20. So now what we can do, this is the first observation for finding figure of merit, and please see this formula. So this side, figure of merit, K equals to, as I told, I by theta, amount of current for unit deflection, I by theta. And from the first equation that is in your copy, I equals to E by R plus G. So it is E by R plus G into theta. This is the value of figure of merit. So from these observations, we have the value of E, we have the value of R, we have the value of theta, and capital G is the galvanometer resistance. Already we have found out. So first table has to be completed, and from the first table you have to find out the value of the galvanometer resistance, and that galvanometer resistance to be put in the second equation. Then we can only find out the value of figure of merit. Okay, K value. Let me tell you, just to give you some idea, let me tell you the values of G and K, because since last few years we are doing the experiments on the same instrument, so we know the value. Like capital G will come almost 54 ohm, 53.26 ohm. Okay, last year we got this 53.26 ohm, so 54 ohm nearly. Okay, this is the resistance for the galvanometer, the galvanometers that we are using. And another one is the K value. K value is almost 1.1 into 10 to the power minus 4. This is ampere per division. This is the value for the figure of merit K, in the order of 10 to the power minus 4. K value, this is the amount of current, very small current, you can understand. For one division deflection, the amount of current is in the order of 10 to the power minus 4 ampere. Okay, 0.1 milliampere, like that. So K equals to this. So these are the values. So whenever you will get the, you will do the experiment, you will get the reading. You can match the values with this. These are the standard values for these instruments which are available in the lab. Okay, so this is all about this experiment. Okay, this way we can, in this experiment we can find out the resistance of a galvanometer as well as the value of the figure of merit. Okay, so these are the two purposes for the, with the same experiment we are doing it. Now this galvanometer, as I told, this is a table galvanometer. There are other types of galvanometer also, d'Arsovale galvanometer. They are the deflection, as we saw here, the deflection is measured by seeing the pointer on the scale. Okay, we have also used another type of galvanometer, d'Arsovale, which is actually fitted on the wall, and there the deflection is observed by lamp and scale arrangement. There is a scale and there is a lamp just below the scale, and light is going and falling on the galvanometer. Inside the galvanometer there is a mirror which is hanging. Okay, and when current is passing through the particular circuit of the galvanometer, the armature is actually deflecting and the mirror is deflecting. So when the light is falling on the mirror, the image is coming on the scale. So the image on the scale will move like this. So that will show the particular deflection. Okay, so you can easily online you can easily search this kind of galvanometer. Okay, lamp and scale arrangement, how does it look like? Okay, or in the class I'll show you, okay, afterwards. So this way different types of galvanometers are there. Here we are using this table, these are commercially known as table galvanometer. So this is the experiment. Now tell me if you have any doubt anywhere in the theory part, in the experimental part. Any doubt if you have, you can ask. Anything you can ask, no problem. I can repeat, not a problem. No doubt is there? So just complete your practical copy, writing the practical copy. These videos we are keeping, if further it can be used, that we'll see. Okay, so this way the classes will be continued. Okay, practical classes, please do attend the classes. Very important, because not only the practical, theory is also there in your syllabus, this corresponding theory. Okay, so this is the experiment related to galvanometer. There are two more experiments with galvanometer, as I discussed, that how to use it as an ammeter, how to measure current with the help of galvanometer, how to measure a potential difference across a resistance using a galvanometer, means how does it behave as a voltmeter. Okay, that way. So there are several mechanisms, so there are certain different experiments that also we'll do in the class like this. Okay, so I think you don't have any doubt. Rakesh, Devanjan, other students who are there, Prakriti, Prithviraj,
Sir, when to write and submit all this?
that you will be informed in the group. Okay, you just keep your practical copies ready. How much you have got in the PDF, you just write it down. Okay,
PDF.
means the PDF that I have posted in the group, all the experiments, so that you just, the
Okay,
writing
okay,
part you
sir.
complete. Keep your copies ready. That is important. Okay, after that you'll be informed by the group, in the group only. Okay, students. So thank you very much. I think you have understood the experiment. Thank you, students.
Thank you, sir.
Thank you, sir.